I'm Dr. B, your chemistry teacher. Today, we are going to look at something good, and that is the relationship between the Gibbs free energy and spontaneity of a reaction. The Gibbs free energy and spontaneity of a reaction. So we're going to see, um, we're going to see the Gibbs free energy, and spontaneity of reactions. Yes, we're going to look at Gibbs free energy and spontaneity of reactions. Quite an interesting topic to discuss. But it's important for us to understand what spontaneity of a reaction is. You know, we said that reactions can be spontaneous and they can also be non-spontaneous. What do we mean? Now, when we say a reaction is spontaneous, what we mean is that the reaction can take off on its own without any necessary additional energy. So a reaction that proceeds on its own without you bringing in any support, whether it's an additional energy or kickstarting such a reaction with a catalyst, or kickstarting such a reaction with any other type of assistance, you classify such reactions to be what? Spontaneous. That means they could begin or start on their own till finish. These reactions are reactions that favor always the product. Remember this, that spontaneous reactions always favor what? The product. But there is something that we must understand, that usually there could also be spontaneous reactions that favor the backward reaction. That is, they favor the reactant. Now, non-spontaneous reactions are reactions that cannot take off by themselves except an additional energy is supplied, or there is an assistance given to such reaction to take off. Maybe a catalyst is introduced to allow the reaction to take off. In that kind of a situation, where a reaction requires some level of assistance to take off, we classify such a reaction as non-spontaneous reactions. You know that spontaneous reactions can either be spontaneous to what? The product, or spontaneous to the reactant. It is when reactions are not supporting the product in terms of spontaneity, we classify them as non-spontaneous reactions. Non-spontaneous reaction could be spontaneous in the backward reaction, like it favors what? The reactant. It is important for us to know that spontaneity of reactions do not depend on whether reactions are exothermic or endothermic. They don't depend on heat changes. So reactions that are exothermic or endothermic can still be what? Spontaneous in nature. We must also understand the fact that spontaneity of reaction does not also depend on rates of reactions or on kinetics of reactions. And that is why reactions that are spontaneous can either be very fast or quick in nature, or can be very, very slow. For example, a common example is a reaction that converts carbon in the form of what? Carbon in the form of diamond to graphite. It is very slow. It takes ages for that to take place. So it's almost a lifetime thing for you to have carbon in the form of a diamond being converted to what? To graphite. It's not as if it's impossible. It is because that spontaneous reaction is very, very slow. Now, if you decide to add water into acid, which is not supposed to be so, you are not supposed to add water into an acid. If you do so, there is going to be an explosion. But supposing you decide to add water into an acid, you get a very fast reaction. It's rather a spontaneous reaction, but you get a very fast reaction, very quick one that could lead to an explosion. You can see the two. One is very fast, one is very slow. But however it is, both of them are spontaneous reactions favoring the product. They do not depend on kinetics, they do not depend on rates of reactions. Now we are going to see how we can be able to tell when a reaction is actually spontaneous and when a reaction is not by looking at the Gibbs free energy. Now let us start with something. Now supposing you have a reaction where the enthalpy of reaction, the change in enthalpy, this is enthalpy, the change in enthalpy of a reaction is positive. That is to say, is greater than 0. Okay? And the change in entropy is also positive. That is to say, is greater than 0. Do you know that if you follow the conventional equation for the Gibbs free energy, which says delta G is equals to delta H minus T delta S, that means if you follow this conventional equation that defines the Gibbs free energy, where delta H is the heat change, like enthalpy, T is the temperature, and delta S is the change in entropy. If you fit these figures into this equation, you will see that your delta G will be negative. That is less than 0. Do you know that the interpretation of this is that exothermic reactions, of course they are what, delta H positive, exothermic reactions will do what? Increase the entropy of a system, will always do what? Will always make such a reaction for that system to be spontaneous. And this will happen only at high temperatures. That means temperature will be what? That means temperature will be high. So it means that for a particular reaction that must be spontaneous, where exothermic reaction is such a reaction, it is going to cause an increase in what? Entropy of the system. And it is only under high temperature you can have that particular reaction, exothermic reaction, to be spontaneous. Then delta G will be negative. So anytime you have delta G negative, it means that that reaction is what? Spontaneous. Now, the interpretation of this, like I said, is that endothermic reaction will do what? Will cause what? Causes an increase in entropy of the system, giving rise to what? Spontaneous reaction. Giving rise to spontaneous reaction at what? High temperatures. That is what it means. That is not a simple thing. So where you have exothermic reactions, just know that they are going to cause what? Cause an increase in entropy of the system. And if they do so, it will only be at higher temperatures that that reaction is going to be what? Is going to be spontaneous. So the delta G means negative, means what the system is, what the reaction is what? Spontaneous reaction. I'm sure we've understood that. Now we're going to look at another scenario. Now, if we look at another scenario where perhaps our enthalpy is rather negative, that is less than 0. Our entropy is negative, that is less than 0. Our delta G is negative, that is less than 0. It is possible, very possible, that where you have an exothermic reaction, because this is the delta H, which is what? Which is negative. So you have an exothermic reaction where heat is given out of the system. It will definitely do what? Reduce what? The entropy of the system. So a reaction that is exothermic, leading to the reduction in the degree of disorderliness of that system, meaning that it turns it to be what? Lesser in terms of instability, it is going to cause the delta G to be negative. The free energy will be negative. Therefore, the system is going to be spontaneous only at low temperature. That means temperature will be what? Low. That's it. So you have an exothermic reaction where heat is given out of the system, leading to what? A reduction in the degree of disorderliness of the system, which is what? Reduced entropy. It will definitely allow the system, allow the reaction to exist as a spontaneous reaction only at low temperatures. So if the system is not experiencing low temperatures, you cannot have such a system to be spontaneous. So with this, we can say exothermic reactions. We say exothermic reactions leading to what? Leading to reduced entropy of system. Entropy of system will always lead to what? Will lead to spontaneity of reaction. Will lead to spontaneity of reaction only at what? Only at low temperatures. So it means that you can only have this kind of a reaction, which exothermic reaction it is, leading to a reduced entropy of the system to become spontaneous only when we have low temperatures for such system. If temperatures are increased, if are higher, okay, it means that you cannot have that kind of a reaction, such an exothermic reaction, to be what? Spontaneous. It takes us back to what we said earlier, that spontaneity does not depend on heat changes. It does not depend on enthalpy. So whether it is exothermic or it is endothermic like the first instance, it doesn't matter. It can still be what? Spontaneous. Now, if we understand this, let's look at the third scenario. Let's look at the third scenario. Let's look at the third scenario. Now, in the third scenario, still trying to look at how the Gibbs free energy can be used to determine spontaneity of a reaction. If enthalpy of a reaction happens to be negative, that is less than 0, and then entropy of the system happens to be positive, that is greater than 0, we'll expect the entropy, the Gibbs free energy to be negative. Now, this is the implication that a reaction that is exothermic in nature, leading to increase in the degree of disorderliness of the system, that is increase in what? Entropy, will always be spontaneous at all temperatures. So it means that at every temperature, or any temperature you use in operating your system, exothermic reactions will always be what? Spontaneous. Exothermic reactions that give rise to an increased entropy will always be what? Spontaneous in any type of temperature that you choose to work with. So what it means here is that exothermic reactions giving rise to increased entropy, increased entropy of system will always lead to what? Spontaneity. Always lead to spontaneity of reaction at all temperatures. So it means that it doesn't matter the temperature you are operating such a system, but in as much as the reaction you want to carry out is an exothermic reaction, which will actually give rise to an increase in entropy, you will always expect what? Always expect spontaneity of that reaction if the temperature is varied at any level, whether it is increased or it is reduced. At any type of temperature, you can always have such a reaction, exothermic reaction, to be spontaneous. Now finally, Finally, we look at another scenario. Now, in this scenario, if your enthalpy is rather positive, that is greater than 0, and the entropy is negative, that is less than 0, we'll expect a positive what? Free energy. If you have an exothermic reaction that will lead to a reduction of the entropy of the system at any temperature at all that you're operating, the system is going to be non-spontaneous. So at all temperature, the system will be non-spontaneous. That's what it means. The system will be non-spontaneous. So at any temperature at all, you decide to operate the system in a much as it's an isothermic reaction that will lead to what? A reduction in the degree of disorderliness of that system, which is the entropy. You will expect that particular reaction to be non-spontaneous at any temperature at all you are operating. So we have seen 4 good scenarios to which we can be able to explain spontaneity of a reaction on the basis of the Gibbs free energy. And I tell you that the Gibbs free energy is the principal thermodynamic parameter among all these parameters that is used reliably in explaining or in determining spontaneity of a reaction, because it is not tied to any condition. I'm sure we've learned something very interesting in today's class. In our next class, we'll take some examples, see how we could solve problems and use the Gibbs free energy in seeing or determining their spontaneity. Until next time, I am still Dr. B. Don't forget to share, to like, subscribe my YouTube channel, follow my Facebook page, make your comments, ask your questions. They will all be attended to at the comment section. It is bye for now.